This lecture, the second one, I came up with 53 slides, and we are not going to do it in 1 hour, it's just not possible. But in the afternoon, we have the tutorial one. So, I will spend the first 1 hour of the tutorial and continue this. Then the second hour, we will just go through the procedure to measure the direct magnetoelectric effect. There are a couple of videos, not long ones, 5 or 6 minutes each. So, I will describe the procedure and then you can view the video. It shouldn't take more than 1 hour. So, this one would be the very basic of all the discussions in this Gian course. So, I want to make sure that we spend enough time for it to understand the phenomena and the measurement procedure. So, we will talk about what are the various ways of measuring the direct magnetoelectric effect, which we define as the response of the composite to a magnetic field, the response in terms of changes in the ferroelectric properties. It can be polarization, it can be dielectric constant, or even the ferroelectric domains under a magnetic field. So, we will discuss the low frequency magnetoelectric effect, and then what happens is you can apply the magnetic field at a variety of frequencies, there is no limit. So, if I have a bulk composite or a layered structure, I change the frequency of the magnetic field. The frequency may be exactly the same for the frequency of acoustic waves. You should be able to excite standing waves in the composite. So, which would mean that the mechanical deformation you produce will also peak. By changing the magnetic field frequency or the electric field frequency, you can excite acoustic waves, which are mechanical waves, leading to very high mechanical deformation. So, you should have the highest possible value for the magnetoelectric coupling coefficient. So, these are acoustic modes. It can be a bending mode or a longitudinal mode. Why would a composite bend? I have a ferromagnet, I have a ferroelectric, agreed? You apply a magnetic field. So, the ferromagnet may shrink, but the ferroelectric does not really respond to a magnetic field. It will try to maintain its length, whereas the ferromagnet will shrink and leading to a small bending, right? It has to. If it shrinks, it will bend up. If the ferromagnet expands, it will bend down, correct? So, if I change the frequency, then I can produce bending waves, like bending acoustic waves, and that can also lead to very high magnetoelectric coefficient. So, you can adjust the frequency of the AC magnetic field or the electric field to produce acoustic waves at bending frequency or longitudinal modes or the thickness modes. You can excite standing waves in the thickness, width, length, or just pure bending waves. All these are resonance modes. That is the way of enhancing the magnetoelectric coupling. Many of the magnetic sensors they use based on this technology, they operate at resonance mode, because if you do not have the resonance mode, the response of the composite is rather small compared to at resonance mode. So, we will look at it later on, but just to give you some idea, we will talk about low frequency magnetoelectric coupling and what happens when you excite these standing waves due to bending or thickness or length or width waves. Okay. Then also I will discuss some models we did for nano-composites and also nonlinear magnetoelectric effects. So, the converse effect is the effect of the electric field on magnetic properties. It can be magnetization or magnetic anisotropy, or you look at the magnetic force microscopy and you look at the magnetic domains, then you apply a voltage or electric field, the domain will undergo a change. You can measure the MFM amplitude or phase based on what happens to the phase or the amplitude under electric field. You can put together estimate of the converse magnetoelectric effect. Okay. So, these are different ways of measuring some of the interaction between the two phases. So, the direct magnetoelectric effect is what happens if I apply, say it can be, you can apply a DC field or an AC field, but we have a lot of interest in what happens under AC magnetic field, because the AC field frequency can change. So, you can come up with depending on the frequency a variety of applications, and that is the reason why we mainly focus on the AC fields. Now, if I apply AC magnetic field, there is a change in polarization, and these two quantities are related through this expression, and alpha is the magnetoelectric tensor. And so, you define alpha with the superscript h, that means you are applying a magnetic field, and that is equal to the change in polarization to the applied magnetic field. And as I mentioned earlier, we measure the voltage coefficient, and that has the unit of volts per centimeter Ørsted, or in the MKS system it is volts per ampere. Okay. That is because if you look at the magnitude, just look at the equation. This is in the MKS unit, delta V is in volts, D is in meters, and H is in amperes per meter. So, that would lead to volts per ampere, that is the unit for the voltage coefficient in MKS system. Otherwise, I usually use CGS, that is volts per centimeter Ørsted, for the voltage coefficient. And the converse effect, it is change in the magnetic induction B or the magnetization in electric field, and you represent this with a superscript alpha E, that is dB dE. So, and you can show that the alpha in the two cases, they are one and the same, they are not different. Okay. And this slide I already showed you, there are different types of composite structures. It can be a bilayer, a multilayer, or a nanoparticle embedded in a host matrix. The particles and the matrix are the two phases, and you can also have a composite structure the way it is shown in this figure, and also you may have nanopillars in a host matrix. And so, for the ferromagnetic phase in a composite, there are quite a few choices. There are really hundreds of them. So, in this talk I am going to discuss composites with 3D transition metals, iron, cobalt and nickel, and rare earths and alloys. For alloys, we will discuss permandur, which is an alloy of iron, cobalt and small amount of vanadium. Med glass is it's an alloy, it's amorphous alloys with iron, boron and a variety of materials. Terphenol D is a rare earth alloy. Galphenol is iron and gallium, And terphenol D and galphenol, they have very good magnetostriction, and they are rather preferred materials for use in a composite for the ferromagnetic phase. And also one could use ferrites. Ferrites are ferrimagnetic, as I mentioned earlier. The magnetic ordering is antiparallel with two different magnetic moments which are not equal. So, there is a net magnetic moment, it behaves like a ferromagnet, and we will talk about ferrites with cubic structure, that these are spinel ferrites, and in that there are quite a few of them: nickel ferrite, cobalt ferrite, nickel zinc, cobalt zinc, and so on. Hexagonal ferrites, they have hexagonal structure, and they have properties which are very unique. They have very high anisotropy field. These are built-in magnetic field in the system, and some of them we are going to talk about are M type. These are different structures: M, Y, Z, and so on. So, we will talk about barium aluminum, strontium aluminum, M type ferrites, cobalt 2 Z and zinc 2 Y. These are Y, Z, and M. They are different types of crystal structures. Okay. Then for the ferroelectrics or the piezoelectrics, we will talk about PZT, lead, barium titanate, lead magnesium niobate, lead titanate. These are relaxer ferroelectrics. And pure piezoelectrics, there are some quartz, langasite, langatate. I'll discuss that a little bit later. So, in the for the ferromagnetic phase, the important parameters are magnetostriction and piezomagnetic coefficient. For 3D metals, iron, cobalt, and nickel, among the three, nickel has the highest magnetostriction and also the piezomagnetic coefficient. What is shown here is the magnetostriction in parts per million, that is 10 power minus 6, versus the bias magnetic field. Lambda 11 is the magnetostriction measured parallel to the field, lambda 12 is perpendicular to the field. So, when we measure the magnetostriction, we use a strain gauge. So, for lambda 11, if this is the sample, the strain gauge is attached to the surface, then you apply a magnetic field parallel to the strain gauge. For lambda 12, the strain gauge is oriented this way, the field is applied perpendicular to it. That is how lambda 12 is. Okay. So, as we see here, lambda 11 is negative and lambda 12 is positive, and usually it is 1/2 of lambda 11. The maximum value here is 15 and the maximum value for lambda 11 is 30. It is 1/2 of that. Okay. That is always the case, but there may be some departure here and there, but it is the rule of thumb is lambda 11 is twice the magnitude of lambda 12 or lambda 13, but there is also a change in the sign. So, the alloy, we will discuss several composites with permandur. It has 49% iron, 49% cobalt, 2% vanadium. It has good magnetostriction, but in the previous case for nickel it is negative, for permandur it is positive. It can be as high as 80 parts per million. Now, also permandur has very high permeability. So, what does it mean? Permeability, higher permeability means the magnetic field can penetrate through the sample very easily. it allows the penetration of the magnetic lines of force. So, the magnetic field will be confined pretty well in the medium. So, that leads to high magnetoelectric coupling. So, anything with high permeability, it is a welcome material for making a composite. Med glass is another material with very high permeability. It can be as high as 100,000. So, med glass is made by what is called rapid quenching. They mix all these metals, iron, cobalt and boron, to make a molten flux, and it is dropped onto a spinning wheel at very high speed. So, the ribbon they pull out, it is amorphous, it is not crystalline, it has very high permeability and pretty good magnetostriction. It is usually in the form of a ribbon, 25 micron in thickness. You can buy a spool of it. It is used in transformer cores because of the high permeability, and we have used it in many of the composites. And also the German group, as I mentioned earlier, they made very good magnetic sensors by combining the med glass with aluminum nitride to make these magnetic field sensors for magnetocardiography. Okay. So, it has very high magnetization, it is about 1.5 Tesla, that is pretty high, and also the magnetostriction is shown here. That is this loop, and the first derivative of that is the piezomagnetic coefficient. That is what is shown here. It goes, it starts from 0 and it goes to very high value, large, and when the magnetostriction saturates, Q goes to 0, because once it saturates, the slope is 0, that is why it is 0. So, this rapid rise in the magnetostriction, derivative of this is it starts from 0, it peaks where the slope is maximum and drops down to 0, and on both it is symmetric. Okay. So, whether you apply a positive field or negative magnetic field, it is always the same sense of change in the length, whereas the piezoelectric coefficient, it can switch from decrease in length to increase in length based on the polarity of the electric field. That does not happen in the case of magnetic field and magnetostriction. But there are materials called electrostrictive. For example, barium titanate is electrostrictive. PM&PT is also electrostrictive. There it is either shrinking or elongation for either both positive or negative electric field. Those are electrostrictive. PZT is piezoelectric, barium titanate and PM&PT are electrostrictive. And in the case of magnetostriction, it is always either positive or negative. It does not matter whether you apply a positive magnetic field or a negative one. This is terphenol D, the series of graphs. It is under different compressive strain applied to the alloy, just ignore it, but just look at the magnitude of the magnetostriction. It is quite high, on the order of a few hundred or 1,000, depending on the magnitude of the magnetic field, and it has terbium and dysprosium and little bit iron. But the problem with terphenol D is it is not easy to machine terphenol D, and it is highly susceptible to oxidation. So, you have to protect the material with some kind of a coating, otherwise it will go bad. It will get oxidized in air and it is gone. Okay. Galphenol, even though it has iron and gallium, gallium is a rare earth, it is not susceptible to oxidation, it has very good, very high magnetostriction, as high as like 250 parts per million, and we have used galphenol also in many of our composites, but the properties such as magnetostriction depends on the amount of iron and gallium in the galphenol. It changes with X. Okay, spinel ferrites, it's an oxide containing iron 3 plus. In all of them, there is trivalent iron. There is also a divalent ion. It can be either magnetic or non-magnetic. Now, just to give you a flavor, the spinel ferrite, it has cubic structure. The lattice constant is around 8 angstrom. The density is around 5.4. But the key factor here is it has two different crystallographic sites for the metal ions. One site is surrounded by 4 oxygen. These are called tetrahedral or A site, that's shown here. The other site is octahedral, surrounded by 6 oxygen. And so the larger ions will try to occupy the tetrahedral site, because the 4 oxygen leaves a large vacant area where a larger ion could fit in, whereas the void left behind between 6 oxygen in the octahedral site is rather small. So, in the case of all the spinel ferrites, the larger ions such as zinc, they always tend to occupy the tetrahedral site, whereas the octahedral site is occupied by iron 3 plus and any divalent substitution such as manganese, cobalt and nickel. So, the magnetic structure is, so you have iron 3 plus also in the tetrahedral site or A site, and they are oriented in the direction opposite to the magnetic moment in the octahedral site. So, for example, this one here, it shows iron 3 plus in A site. This is a metal ion. It can be manganese, cobalt or nickel, and these moments will be aligned parallel to each other, but opposite to the moment in the A site. So, the net moment arises, it is equal to the difference between the two. And they have very high Curie temperature, 600 to 900 degrees Celsius. So, any device you make with spinel ferrites, they can work at much higher temperature compared to other choices such as iron, cobalt and nickel. If you go to very high temperature, they get oxidized, they will go bad, whereas these are already oxides, they have pretty good Curie temperature, and you don't have to worry about oxidizing any metal. Okay. And they have decent magnetization at room temperature. Permeability is anywhere from 100 to 100,000, especially manganese ferrite, it has very high permeability. And also, when you put together a device operating at high frequencies, such as microwave or millimeter waves, you would rather use a ferrite because it has low losses at high frequencies compared to metals. They have very high losses at high frequencies. These are eddy current losses, and you are familiar with eddy currents. I am sure that when the frequency goes higher, the eddy current losses go higher too. And this is the structure for when I substitute zinc in some of the ferrites, for example, nickel ferrite, it has some unusual properties in the sense that zinc will prefer to go to the tetrahedral site, so it will knock some iron from tetrahedral to octahedral site. So, you can increase the magnetization for the ferrite by substituting a non-magnetic ion, and also it has little bit higher magnetostriction and higher piezo-magnetic coefficient, but I do not want to confuse you with too many details. Take it for granted that if I substitute zinc in nickel ferrite or cobalt ferrite, two things happen. One is there can be an increase in the magnetization and in the magnetostriction for zinc substitution up to 0.3. So, these are preferred composition for use in some of the composites. So, hexagonal ferrites, they have hexagonal structures, and it can be a whole variety of structures like M type, Y and Z, but I do not want to go into the detail, but you will get to see the structure later on. But what is important here is that the M type, such as strontium hexaferrite or barium, it has very high magnetocrystalline anisotropy, and M type it has uniaxial. So, what is preferred about using these is that when you put together a composite, for example, you want to make a magnetic sensor. Okay? So, a magnetic sensor that capable of measuring an AC magnetic field will have a ferromagnetic phase and a ferroelectric phase, correct? Now, okay, look at this. For example, this is magnetostriction versus bias magnetic field. Now, if I do not apply any bias magnetic field, but I apply an AC field at 0 bias. Look at this, what happens if I apply an AC field at 0 bias? Is there any AC mechanical strain? No. Just imagine like this is the so this is the response, magnetostriction versus bias field. So, applying an AC field here without any bias would mean that you are applying an AC magnetic field at this point. So, corresponding mechanical deformation, there is nothing. On the other hand, if I apply an AC magnetic field at 100 oersted of bias field, then the AC magnetic field will vary like this. The corresponding mechanical force will be something like this, correct? So, that would mean that to realize a sensor of AC magnetic field, you prefer a bias magnetic field, okay? That is understood. If I want to put together a sensor array for magnetocardiography, each sensor element must have a bias field. So, you have to have a magnet associated with each element. So, in an array you may have 100 or 1000 sensor elements, and each one will have its own magnet. That is a mess. There will be cross-talk between these magnets that will ruin the whole sensitivity, and the whole system goes, it is not going to serve the purpose, it is waste of time. So, what you could do is, you can make a sensor element which is self-biased. So, that means there is a built-in magnetic field in the composite itself. That is where the hexagonal ferrites are key element in this whole scheme. So, if I have strontium or barium hexaferrite with a very high uniaxial anisotropy field, so it has a built-in magnetic field which will act as a bias field. So, that will eliminate the need for an external permanent magnet or something else. So, that is how you overcome these difficulties with the use of hexagonal ferrite. So, M type has uniaxial anisotropy field, it is very high, it can be 17 to 30 kilooersted, and the Z and Y type they can have in plane anisotropy little bit less than M type, like 9 to 10 kilooersted. And for the ferroelectric, there are several choices. Barium titanate, as I mentioned earlier, that it's electrostrictive. This is the piezoelectric coefficient as a function of applied electric field. Whether it's positive field or negative field, the strain is still the same, it doesn't change sign. And this is typical polarization versus electric field. For barium titanate, it has cubic structure above the ferroelectric transition. So, when it goes through ferroelectric transition, the barium is slightly displaced, so that the center of positive and negative ions will have a separation. So, that will produce a dipole moment, and that is how it becomes a ferroelectric. So, PZT is a combination of lead zirconate and lead titanate, and at the morphotrophic phase transition corresponding to this composition, it has very high piezoelectric coefficient, and this is the traditional D33 or strain versus electric field. So, it starts with 0, goes high, it can be like as high as 0.2%. Then as you come back in electric field, the polarization can suddenly switch, and the strain it can become from tensile to compressive. That is what it means. Compressive means negative, tensile is positive, but it can be both positive and negative, whereas barium titanate it can be only one sense. So, the D value is on the order of 200 to 600 picometers per volt for PZT. So, it is very easy to make, and it is not expensive. You can get it for few pennies for some of these, but you want to stay away from lead because of its contamination, and especially small children, it's very damaging to their brain development. So, they want to stay very low on lead content in drinking water. In the States, they found that many of the pipes are made of lead, and they poison the water pretty much. And one city in Michigan, Flint, and they used contaminated water because they switched from river water to local water, which was more acidic. So, it leached more lead into the drinking water, and many children were affected. So, they ended up spending millions of dollars cleaning up the water system, and it is okay now. So, lead, you want to stay away from it if at all possible, but they are still, PZT is still used in many of the applications, and we use in many of our composite systems. PM and PT, it's a relaxer ferroelectric. The difference between PZT and PM and PT is that in the case of PM and PT, the transition from paraelectric to ferroelectricity, it occurs over a wide temperature range. It's not very sharp, it's rather slow, but apart from that, it has very good piezoelectric coefficient on the order of several thousand, the dielectric permittivity is also quite high. So I want to point out here that the ratio of d to epsilon, 2000 divided by 3000, it's 0.66. And some of the pure piezoelectrics such as quartz, they have comparable value. So you may use rather quartz than PM and PT because quartz doesn't have any lead in it. So it's not going to be a problem with cleaning up the environment compared to PM and PT. And these are the piezoelectrics that we used in some of our studies. Lanthanum gallium tantalate. So these are called langatate, LGT. Langasite is the tantalum is replaced by silicon, that's LGS. You could also use quartz and also aluminum nitride. Gallium arsenide is a piezoelectric. People have used gallium arsenide and gallium nitride. Gallium nitride is used in many of the semiconductor devices for IC chips. So you could use also in the magnetoelectric device if you put together a gallium nitride and a ferromagnetic composite. It can also act as a magnetic sensor. So you have a semiconductor device on a gallium chip, and then simultaneously you can put together a magnetoelectric device. And the advantage with piezoelectrics is that you don't have to worry about this is polarization versus electric field. There is a hysteresis, there is a loss associated with it. If you look at the polarization for a dielectric, it will be a straight line through the origin. It's a straight line. The dielectric, the piezoelectric coefficient is also it's linear, and there is no hysteresis loss, and they are also very good at, for use at very high temperature. Whereas in a ferroelectric, you have to worry about what is the ferroelectric Curie temperature. You cannot operate the device close to the transition temperature, or it's impossible to use it above the transition temperature. Whereas a piezoelectric such as quartz, it's good to go even at very high temperatures. All right, so we will talk about now measurements of direct magnetoelectric effect and the theory. I don't want to go into too much mathematics. There are some equations. I just point out what the important factors are. Apart from that, there is no need to go through the first principles calculation. Okay. And here is a simple setup to measure the direct magnetoelectric effect. That's the influence of a magnetic field on the ferroelectric phase. And what you need is, you have to apply for the voltage coefficient a bias magnetic field and AC magnetic field. You can apply a bias magnetic field with a solenoid or an electromagnet or a permanent magnet, doesn't matter. With a permanent magnet, the field is constant, but if you want to measure it as a function of bias magnetic field, then you must use an electromagnet or a solenoid. The AC magnetic field can be produced by a pair of Helmholtz coils. The measurements can be done for a variety of field orientations. What's shown here is two orientations, one which I call transverse. In this case, the ferroelectric phase is pre-poled. You align all the electric dipoles perpendicular to the length of it. So the poling is in this direction, right? Then you apply the DC magnetic field and the AC field parallel to the plane of the bilayer. So this is dimension 1, dimension 2 is the width, dimension 3 is the like XYZ, this is perpendicular to the bilayer. So, alpha E31 would mean that you are applying the magnetic field both AC and DC along direction 1, and you measure the voltage across the thickness of the piezoelectric phase. Okay? And in the second case, all the fields are perpendicular to the bilayer. The electric field, the polling is done in this direction. The AC and DC magnetic fields are also along direction 3, and then you measure the induced electric field or the voltage in this direction. That is all that. So, how do you calculate the voltage coefficient? The basic equation is the strain at the interface. This is the interface between the ferromagnet and the ferroelectric phase. That is given by this equation. The first term is the elastic effect. The T is the stress tensor and the compliance coefficient. Compliance is inverse of Young's modulus. And the second term is the piezoelectric effect, that is D times E. The third term is the piezomagnetic effect, that is Q times H. So, the way it is done is you estimate the magnetoelectric coefficient with this 3-step procedure. The first step is to estimate the total strain at the interface, which is the sum of the elastic, and if it is an electric field, it is piezoelectric strain. If it is a magnetic field, it is magnetostrictive strain. So, you find this term S, then you have to estimate the strain stress relationship at the boundary between the two phases, and then you can estimate the the electric field stress electric field relationship, and also the boundary conditions are important. The bilayer can be free to expand along the direction 3, or if you clamp it, the boundary condition will change. Okay. And this is the equation under if the bilayer is free to expand in the direction 3, this is the equation. Q is the piezomagnetic coefficient, and look at this, it has two terms, Q11 and Q12, because when you apply a magnetic AC field parallel to the sample plane, there is change in the length in this direction as well as in the perpendicular direction, right. That is Q11 and Q12. Those are the two terms. And D31 is the piezoelectric coefficient that is important is D33, because the ferroelectric phase is poled in this direction, but the term that couples to the magnetic field is D33, but D31 is the coupling term to any change in the length and the width of the ferromagnet due to the magnetic field. So, those are the different terms, and also you have S is the elastic coefficient for the piezomagnetic phase and the piezoelectric phase, and this V is the amount of the two phases, like 1 minus V is if V is the amount of volume fraction for the PZT, 1 minus V is the volume fraction for the ferromagnetic phase. So, it is a bit complicated expression, but what it comes down to is these are the key terms Q and D. So, this is the piezoelectric coupling coefficient. It couples to what happens due to the in-plane AC magnetic field. And the one here is for all the fields perpendicular to the plane, and these are some examples for very selected system of bilayer composites. The So, we are considering a bilayer of a ferromagnet and a ferroelectric. So, these theoretical curves are for the ferromagnetic phase being a spinel ferrite, in this case a nickel ferrite. The ferroelectric phase is PZT. There are known parameters. You can estimate the Q values and D values which are given in the literature, or you can take the measured values and come up with these theoretical estimates. What is given here is the magnetoelectric voltage coefficient under two conditions. One is the bilayer is free, or the bilayer is clamped with an external force. You can take for example, you can take a bilayer and then clamp it with a C clamp, or any type of mechanical force to squeeze it, or you clamping you can do it with just putting the composite between two fingers and then make sure that it doesn't have the power to expand or contract in the perpendicular direction. When you do that, the boundary conditions at the interface will change. That will change the magnetoelectric voltage coefficient. As you see here, when it is rigidly clamped, the voltage coefficient is much higher compared to unclamped in this particular case. What is along the x-axis is, in this composite, how much PZT and how much ferrite is present. This V is the volume fraction for the piezoelectric phase. If the volume fraction is 0.2, that means it is 0.2 for PZT, 0.8 for nickel ferrite. Okay. So, it peaks around 50-50, that is what the peak value is. So, when the composite has equal volume of nickel ferrite and PZT, that is when the response of the sample is maximum. And also you see here that rigidly clamped and free unclamped samples, they have different response to an applied magnetic field. And these are in plane magnetic fields. This one is magnetic fields perpendicular to the plane, and this one is in plane longitudinal. The PZT is poled in this direction, all the magnetic fields are also in this direction. You measure the voltage across this direction. Okay. And I haven't seen any experiment for this particular geometry. And these are for similar graphs for cobalt ferrite, barium titanate, and once again it's for three different orientation for the fields. The top one is for in-plane magnetic field, the middle one is for out-of-plane magnetic fields, and the third one is for all the fields parallel to the sample plane. And lanthanum strontium manganese oxide, it's a ferromagnet. The interaction that leads to ferromagnetism in this case is different from ferrites. In spinel ferrites and hexagonal ferrites, it's a super exchange interaction that leads to the magnetic ordering. And this one has what's called double exchange, but you don't have to worry about it now. But I want to make sure that you understand the key difference between this oxide, which is ferromagnetic, versus the spinel ferrites, which are ferrimagnetic, or hexagonal ferrite, because it has super exchange, this is double exchange. Okay. It's ferromagnetic, but the Curie temperature is very small, close to room temperature, and this is not the material you want to use in a composite, because it will lose its coupling just slightly above room temperature, and you don't want to use it if you can. So, this is something I want to show you this afternoon, I will show you the measurement system that we have in my lab, and it's very similar to what is shown here. To measure the voltage coefficient, you need a bias magnetic field. So we have an electromagnet to do that, and then the AC magnetic field is produced by a pair of Helmholtz coil. The sample is placed here so that the fields are all in this particular case. You can orient the sample parallel to this field, or you can turn it by 90 degrees to make it perpendicular to the field. Then the DC power supply will drive this electromagnet, and the AC power supply will drive these Helmholtz coils. Then you measure the voltage across the sample, the ferroelectric layers. There are many ways to measure the voltage. You can use an oscilloscope, or you can use a lock-in amplifier. A lock-in amplifier will lock onto a particular frequency. So that would eliminate any noise pickup. So if you know the frequency of the magnetic field you are applying, then you can lock the voltage measurement to that particular frequency. So it will give you a clean measurement. It won't have fluctuation because of noise pickup. There are other ways to reduce the noise. In our case, these Helmholtz coils are enclosed in a metal box which will shield the Helmholtz coil from picking up any RF radiation from outside sources. That will also reduce the noise. Now, so when you make the measurement, the voltage coefficient is proportional to the product of Q and d over epsilon. Q is the derivative d lambda dh. What's shown here on the right is lambda versus h. D lambda dh is, you are taking the first derivative of this, and this is what is shown in the middle one. Then the bottom one is what you would measure if you change the amplitude of the AC magnetic field. And if you do that, it's a linear function, and the voltage will increase linearly with the applied AC magnetic field. If you take the slope of this, that is the voltage coefficient times the thickness T. You take the slope, divide by the thickness of the composite or the PZT, then you have the voltage coefficient. Okay. So that's what is shown in this particular example. We put together a multi-layer of nickel ferrite and PZT, and this one had 16 layers of nickel ferrite, 15 layers of PZT, so the total is 31 layers. Each layer is 15 micron in thickness. So we made these ferrite and PZT by what's called tape casting. It's a lengthy process. Then in the tape casting you make these layers separately, the ferrite and PZT. Then you stack them up the way you want. Then just in sequence, nickel ferrite PZT, nickel ferrite PZT. So you build this multi-layer, then you can press it in a hydraulic press, then you can center it at high temperature. Then what you get is a pretty good multi-layer sample, and that's what we had. Then we measured the voltage coefficient. As you see here, as you increase the bias voltage, this is for a constant amplitude of the AC magnetic field applied at 100 hertz, and these are the voltage coefficient for magnetic field, both AC and DC, parallel to the sample plane, and it was initially pole perpendicular. So the voltage was measured across the thickness. The voltage coefficient is in volts, millivolts per centimeter Oersted. It starts with 0, keeps going up and up until it peaks where the slope is maximum. then it keeps going down because you are going above this maximum slope. It keeps going down, down, and then ultimately it goes to zero when the magnetization, when the magnetostriction saturates. This is for in-plane magnetic fields. This is for magnetic field perpendicular to the plane. As you see here, the magnitude for this case is much smaller than in-plane magnetic field. That's because when you change the orientation of the magnetic fields from parallel to perpendicular, there is demagnetization. Both the AC field and the DC field will decrease because of the demagnetizing field. So the overall effect will be weaker, and that's what is shown in this data. And then we considered in the model a series of nano-composites, nano bilayers and nano pillar, nano wire, and it's a series of theory. And let's go through quickly, and I don't want to spend too much time because we don't have very many experimental data to compare with the theory. That's one thing. Number two, in the theoretical model that we came up with, we used the parameters for the magnetic phase and the ferroelectric phase that corresponded to bulk materials. But when you go from bulk to nano, everything changes, all the properties. But we didn't have the experimental values for all these parameters such as magnetostriction and the piezoelectric coefficient. So we ended up using bulk values that will lead to very high overestimates for the theoretical values. So you have to take these values with a pinch of salt. They are not reflective of the reality. It's something imaginary. Okay, just to warn you. Now what's shown here is a bilayer of PZT and nickel ferrite on magnesium oxide substrate. V sub S is what is the volume of the substrate or the thickness. The first very top corresponds to no substrate whatsoever. So it's a freestanding bilayer and it has the maximum value for the voltage coefficient. As you go to a larger volume for the substrate, the value keeps going down. If the substrate volume is 10 times the volume of the bilayer, see how low it is. The reason being, if you have a substrate, the films will not respond to either the magnetic field or the electric field freely. They have a clamping effect to the substrate. The substrate will not allow them to freely expand under the magnetic field, for example. So there is clamping effect, and overall effect will be weaker compared to a freestanding bilayer. Okay. This is for a nano pillar in a host matrix. These are pillars of PZT in a host of nickel ferrite, and the nano pillar is on a substrate. Once again, there are parameters corresponding to the substrate, or here is the radius of this substrate, and then L sub m is the height of this nano pillar. Ls is the thickness of the substrate, and we assume magnesium oxide. Now, when the substrate radius is much smaller than the length of the nano pillar, the clamping is rather weak, but when it is comparable, there is significant reduction in the magnetoelectric coefficient because of the clamping effect. And this one is coaxial nanowire on a template. Here the template is magnesium oxide, that is this cylindrical substrate, and nickel ferrite and PZT, they are grown sequentially on the substrate. So, you have nickel ferrite layer, then you coat it with lead, PZT. So, it is a coaxial nanowire on a template. Once again, when there is practically no template, there is very weak clamping effect. So, as the template grows in radius or in volume, there is clamping effect. So, there is a decrease in the voltage coefficient, and the two cases here, the previous ones, nanopillar in a Hauss matrix or a coaxial nanowire on a template, they are approximately same magnitude for the voltage coefficient. Okay, shall we stop here? Okay, so in the afternoon, the very first hour, I will discuss the rest of this particular talk, then go over to the demonstration of the measurement of the low frequency magnetoelectric effect. Okay, all right, yeah. Thank you. Questions? I think they are tired. Yeah. All right. Yeah.
So why there is a need of superimposing of AC as well as DC magnetic field? Means I want to ask, is there any difference of output voltage with AC magnetic field and DC only DC magnetic field by measuring the voltage?
So you want to apply only the AC field?
No.
And no DC field?
So why both magnetic field are required?
Why? Okay. You can apply a DC field, that's fine. So when you apply a DC field, there will be a change in the polarization. But the piezoelectric layer has a finite conductivity. Even though we say it's infinite, it's finite. So there will be what's called a leakage current. So the voltage builds up. So the leakage current will bring the positive and negative. They will be annihilated. You lose all the voltage. There's nothing to show for, right? Whereas if you apply an AC magnetic field, there's a switching of polarity, then there is a real AC field, AC voltage that you can measure. It's not going to go to 0. Whereas in the static case, DC field only, the voltage will die down to 0 and you don't have anything.
Multi-layers, 15 layers, stack layers of composites. So you said you will how will you polarize that composite?
Okay, I will show you how to polarize it in the afternoon. So it's very easy to polarize because all you want to do is you heat up the whole composite, apply an electric field.
It will affect the magnetic properties.
No, because the ferrite has high enough Curie temperature. When I heat it up, it's only 100 degrees, whereas Curie's temperature is 600 degrees. So it won't affect the magnetic phase.
If you apply the field also can disturb the magnetic.
Magnetic field, you don't have, you are applying during the measurement, right? So it's there. So the only thing is you have to align all the electric dipoles perpendicular to the plane. That you can do by heating it up to maybe 100 degrees, apply a large voltage, several thousand, then cool it back down to room temperature. We let it stand for several hours. So at the end of the day, you have a poled PZT. And many of the bilayers that we use, we can buy PZT already pre-poled from the vendors. They sell it pre-poled PZT, that's rather easy.
So once polling is done, how long it?
Yeah, that's a good question. That's also I'm going to address in the afternoon. There will be some relaxation. You lose the effect in terms of decrease in D33. So it will be 3 or 4%. And some of the PZTs that we got commercially, they are still good after many years. They are not going to die down overnight. but they do decrease with time.